Welcome back to Cooperative AI Notes. This is our second deep dive, and we're really aiming this at you if you're keen on understanding the building blocks for safe AI.
Yeah, last time was more of a broad overview. Today, we're going to drill down into some really fundamental machine learning concepts, stuff you really need to know for advanced AI, especially cooperative AI.
Absolutely. And we've looked at, quite a range of materials, videos, academic papers, discussions, trying to piece together the essentials for you.
Our mission today really is to give you a solid, clear understanding of reinforcement learning, neural networks, and of course, large language models. These are like the key ingredients in so much cutting-edge AI.
Okay, let's jump right in then. Reinforcement learning, RL. Basically, it's teaching an agent, like a program, to make decisions.
Right. It learns by interacting with some kind of environment, it tries stuff, and it gets rewards or penalties based on what happens. It's learning what to do to get the best cumulative outcome.
So it's different from, say, supervised learning, where you just give it labeled pictures of cats and dogs.
Exactly. Supervised learning has the answers provided, and unsupervised learning is about finding patterns in data without labels. RL is unique because the learning happens through this active trial and error, this interaction driven by rewards.
Got it. Now, there's a key term in RL, the policy, usually written as pi, the Greek letter. What's that about?
The policy, yeah. Think of it as the agent's strategy or its rulebook. It tells the agent what action to take depending on the situation or the state it finds itself in.
So it maps states to actions.
Precisely. And the whole goal of RL, really, is to find the best policy, the one that maximizes the total reward the agent expects to get over time.
Okay, makes sense. But it sounds like it could be slow. I've heard about sparse rewards. What does sparse mean here?
Sparse rewards are a big challenge. It means the agent only gets that feedback, that reward or punishment very infrequently. Often, like only right at the very end of a long task.
Yeah. Like winning a chess game. You only know you won at the final checkmate, not after each move.
Exactly. Or imagine a robot trying to navigate a maze. It might only get a reward when it finally finds the exit. All those turns it made along the way, no immediate feedback.
That must make learning incredibly hard if you don't know which steps were good until the very end.
It does, and that leads directly to what's called the credit assignment problem.
Credit assignment. Okay, let me guess. It's hard to assign credit to the right actions.
You got it. If the reward only comes after, say, 100 steps, how does the agent figure out which of those 100 steps were the crucial ones? Which specific turns in the maze actually led to the exit? Assigning credit or blame correctly is really tough with delayed rewards.
Yeah, I can see that. Which brings up another term, sample efficiency. What's that measure?
Sample efficiency is all about how much data, how much experience the agent needs to learn a good policy, how many times does it have to interact with the environment, try things out.
So low sample efficiency means it needs tons and tons of tries.
Right. Some environments or reward setups just require a huge amount of interaction before the agent learns effectively. It can be very data hungry.
Are there ways around that? I think I heard about model-based RL.
Yeah, model-based RL is one approach. The agent tries to learn a model of how the environment works, kind of like its own internal simulation. This can sometimes help it plan better and learn with less raw experience, improving sample efficiency.
But it sounds like there's a catch.
Well, the catch is that the learned model might not be perfect. If its understanding of the environment is flawed, its planning might go wrong. So it's a trade-off.
Okay, so dealing with sparse rewards and maybe improving sample efficiency. This leads to reward shaping, right? What is that?
Reward shaping is a technique, yeah. It's where we, the designers, try to help the agent out by adding extra intermediate reward signals.
So not just waiting for the final big reward.
Exactly. We give it little hints or nudges along the way to guide it, especially when the main reward is sparse. It makes the learning signal less sparse, basically.
Can you give an example, like back to the maze?
Sure. In the maze, instead of only rewarding the agent for reaching the exit, we could maybe give it a small positive reward every time it takes a step that moves it closer to the exit.
How would it know it's closer?
We might use something like, say, the distance to the goal. You could define a potential function, often called phi, for each state as, maybe based on negative distance, and reward the agent for increasing this potential.
It sounds really clever, like putting up signposts. But are there dangers?
Oh, definitely. The big one is called reward hacking.
Hacking, like cheating the system.
Sort of. The agent finds a way to maximize the shaped reward we gave it, but without actually achieving the real goal we intended.
Uh-oh. Like what?
Well, in that maze example, if we just rewarded moving closer, maybe the agent finds a spot near the exit, but just moves back and forth across the boundary to keep getting the getting closer reward without ever actually going in.
Huh. Okay, so it finds a loophole in the reward rules.
Exactly. It highlights how carefully you have to design these reward functions. You need thorough testing to ensure you're actually incentivizing the behavior you want, not some weird side effect.
That's a really important point. Okay, so RL is about learning from interaction and rewards, dealing with sparsity and credit assignment. Let's shift gears. Neural networks. We hear this term all the time. What are they fundamentally?
Fundamentally, they're a type of machine learning model that's loosely inspired by the structure of the brain. They consist of layers of interconnected units, usually called neurons.
Layers. Okay, what kinds of layers?
Typically, you have at least three kinds. First, the input layer. That's where the raw data comes in. If it's an image, maybe each input neuron corresponds to a pixel's brightness. For recognizing handwritten digits, like a 28 by 28 pixel image, you'd have 784 input neurons.
Okay, data goes in.
Yeah. Then you have one or more hidden layers. These are the intermediate layers where the actual computation, the processing, happens. The number of layers and neurons in each can vary a lot. Maybe 2 hidden layers with 16 neurons each for a simple task, or many more for complex ones.
Hidden because we don't directly interact with them.
Pretty much, yeah. They're between the input and the output, and finally you have the output layer.
Which gives the answer.
Right. It produces the final result. For digit recognition, it might have 10 neurons, one for each digit from 0 to 9, outputting a probability for each.
So how does the information actually flow through these layers, from input to output?
Okay, so each neuron in a layer gets signals from the neurons in the layer before it. These incoming signals are multiplied by weights.
Weights, like how important is that connection?
Exactly. A weight represents the strength and direction, positive or negative, of a connection. A higher absolute weight means a stronger influence.
Just weighted signals.
Almost. After summing up all those weighted inputs, the neuron usually adds another number called a bias.
A bias. What does that do?
The bias kind of shifts the activation threshold. It makes it easier or harder for the neuron to fire or become active. Then this whole sum, weighted inputs plus bias, goes through an activation function.
Activation function.
Like sigmoid.
Sigmoid is a common one, yeah. It squishes the value into a range, often between 0 and 1. This introduces nonlinearity, which is really important. It lets the network learn complex patterns, not just simple linear relationships. The output of this function is the neuron's activation, which gets passed to the next layer.
And the network learns by changing these weights and biases.
That's the core idea. Learning involves adjusting all those weights and biases throughout the network. The goal is to minimize a cost function.
Cost function that measures how wrong the network is.
Precisely. It compares the network's output for a given training example to the actual correct answer and calculates an error, or cost. We want to make this cost as low as possible across all training examples.
How does it know how to adjust them? Which way to tweak the numbers? That's where an optimization algorithm, most commonly gradient descent, comes in.
Gradient. Like a slope.
Exactly. Imagine the cost function as defining a landscape with hills and valleys. Gradient descent tries to find the lowest valley. It calculates the gradient, the direction of steepest slope of the cost function, with respect to each weight and bias.
And then it moves downhill.
It takes a small step in the opposite direction of the gradient, the direction that reduces the cost the most. It repeats this iteratively, step by step, hopefully converging towards a set of weights and biases that result in a low cost.
Okay, and one more term here. Backpropagation. What's its role?
Backpropagation is the engine that makes gradient descent efficient for deep networks. It's a clever algorithm for calculating those gradients, the slope of the cost, with respect to every single weight and bias in the network.
How does it work, roughly?
It uses the chain rule from calculus. It starts by calculating the error at the output layer, and then it propagates this error signal backwards through the network, layer by layer. This lets it figure out how much each weight and bias in the earlier layers contributed to the final error.
So it efficiently tells gradient descent which way to adjust everything.
Exactly. It's the key algorithm that allows neural networks to learn effectively from their errors, especially when you have many layers.
Great. That makes neural networks much clearer. Now let's talk about the really big ones. Large language models, LLMs. What makes them large?
Well, the name gives it away. They are large. They are a type of neural network, but they have an absolutely massive number of parameters, those weights and biases we just talked about. We're talking billions or even hundreds of billions. Llama 270B, for example, has around 70 billion parameters.
70 billion.
Yeah.
And they're trained on huge amounts of text.
Huge is an understatement. They're trained on vast quantities of text data, mostly scraped from the internet. Think trillions of words. It could be like 10 terabytes of text data.
Training that must be intensive.
Yeah, extremely. It requires enormous computational resources, think thousands of specialized processors like GPUs, running continuously for weeks or even months. And it costs millions of dollars just for that initial training phase. For Llama 270B, it was something like 6,000 GPUs for 12 days, costing around $2 million.
Okay, so after all that effort, what does a base LLM actually do? What's its core function?
At its absolute core, a base LLM is trained to do one primary thing: predict the next word in a sequence. Given some text input, it calculates the probability distribution over all possible next words.
Just predicting the next word, that seems too simple to explain things like writing essays or code.
It does seem simple, but that's the fundamental mechanism. By repeatedly predicting the next most likely word, given the context of the words generated so far, it can produce surprisingly coherent, complex, and contextually relevant text. Its entire behavior is determined by those learned parameters encoding these next word probabilities.
So those billions of parameters are like a compressed version of the internet text it learned from.
That's a pretty good analogy, yeah. It's like a very lossy compression, a zip file of the patterns, relationships, facts, and even biases present in that massive training data set. It captures a kind of gestalt of the information.
But we don't fully understand how it represents that information internally.
Not really, no. That's the whole field of interpretability research. Trying to understand what's actually going on inside these incredibly complex networks is a major ongoing challenge. We see the impressive outputs, but the internal reasoning, if you can call it that, is still largely a black box.
Okay, so we have this base model trained on the internet, but then we hear about fine-tuning. Why is that needed?
Right. Building a useful LM usually involves two main stages. First is that base training or pre-training that we just discussed.
That builds the general knowledge?
Exactly. It learns language, facts, basic reasoning patterns from that huge data set. The result is a powerful but general-purpose base model. Then comes the second stage, fine-tuning.
And fine-tuning makes it more specific.
Precisely. You take the pre-trained base model and train it further, but this time on a much smaller, more curated data set designed for a specific task or behavior.
Like what kind of data?
It could be question and answer pairs if you want a Q&A bot, or dialogue data to make it better at conversation, or maybe examples following specific instructions or text written in a certain style.
So fine-tuning is like changing its focus or its style.
Yeah, you can think of it as changing the model's formatting or behavior. It adapts the model from being a general internet text predictor to something more specific, like a helpful assistant that answers questions clearly or follows instructions reliably.
But it still uses the knowledge from the first stage.
Absolutely. It retains all that broad knowledge learned during pre-training, but learns how to apply it or present it in the desired way based on the fine-tuning data. And techniques like reinforcement learning from human feedback, RLHF, are often part of this fine-tuning process.
RLHF. Using human feedback to guide the RL.
Kind of, yeah. Humans rate different responses generated by the model, and this feedback is used to train a reward model, which then helps fine-tune the LLM using reinforcement learning to make its outputs more aligned with what humans prefer: helpful, honest, harmless.
That connects back nicely to RL. Okay, this really helps understand the journey of an LLM. So just to wrap up this deep dive, we've covered reinforcement learning, the basics of neural networks, and how these massive LLMs are trained in stages.
And these aren't just abstract ideas, right? They are the core mechanisms behind how many advanced AI systems learn, decide, and interact. Understanding policies, rewards, credit assignment, how networks learn through weights and biases, and how LLMs gain knowledge and then get fine-tuned. It's all crucial background if you're interested in building AI that's safe and works well with us.
Yeah, it's fascinating how these pieces fit together. Using RL to train a policy that's actually represented by a neural network, and then seeing how LLMs, after fine-tuning, can understand instructions and potentially even navigate cooperative situations.
It really brings up a key question, doesn't it? Especially for you listening. As these systems get more powerful, How do we design those reward functions? How do we select that fine-tuning data to make sure they learn to be genuinely cooperative and aligned with human values?
That is the big question, really. Something definitely worth pondering. Well, we hope you'll join us for our next deep dive in cooperative AI notes. We'll be building directly on this foundation and shifting focus towards the critical areas of AI safety, ethics, and governance.